Hi, and this is the first part of a six-part series that I will be doing for my exam 3 submission for my transport class. And this series is about basically simulating a time varying temperature profile in a uniform bar. So in the first part, this video, what we want to do is we want to show that this function, as we have written here, is a solution to the time-dependent heat diffusion equation with no heat generation. And we'll be able to do that by using von Neumann's stability analysis, as well as Euler's formula, which is where this solution comes from. So again, to be able to do this, we're going to be using von Neumann's stability analysis. So what that is it is a partial differential equation which states that the partial derivative of temperature with respect to time is equal to the thermal diffusivity times the partial derivative, well, the second derivative of the temperature with respect to position. And again, I want to note Euler's formula, which is E times I to the X is equal to cosine of X plus I times the sine of X. And I is just an imaginary number. So we stated that a solution to this partial differential equation is T equal to I times KX times E raised to the power of the negative thermal diffusivity times K squared T. And again, I is just an imaginary number and K is an arbitrary integer. So it doesn't really mean much. It's a variable. And to be able to prove that this is a solution, all we have to do is plug it in. So when we do that, on the right-hand side or the left-hand side, all we do is take the first derivative. So that gives us negative thermal diffusivity times K squared times E to the negative thermal diffusivity times K squared T. And that is multiplied by E to the IKX. And then on the right-hand side, taking the second derivative with respect to position, we get the thermal diffusivity multiplied by E to the negative thermal diffusivity, K squared T times I squared K squared E to the IKX. And we notice here that I squared is just equal to -1 since it's an imaginary number. And that in turn gives us this expression, which is just by simplifying, knowing that, which is equal to the left-hand side and therefore proving to be a solution of the partial differential equation.